Okay, so welcome to the lecture video on tropical cyclones. Sorry that this got posted so late, but without further ado, there's a lot to get through, so I'm going to get right into it. So, tropical cyclones are intense warm core, meaning that the centers of the system are warm, rather than most mid-latitude cyclones, which are cold core, cold circulations in the center. Low pressure systems with heavy winds, strong winds, heavy rains, and as a tropical cyclone, they're from the tropics. They can also cause high ocean waves, damaging storm surge, and tornadoes as particular hazards of note. And there's different names that we give to tropical cyclones depending on where they're located, which oceanic or tropical basin they come from, and their strength intensity. So some of these names that we go through, tropical depression is what we call an organized system of clouds, this tropical system of the clouds and thunderstorms with a defined closed surface circulation, so it's actually organized, but it's relatively weak. The maximum sustained surface winds are less than 39 miles per hour. A tropical storm is once it actually gets up to a certain intensity threshold where it's an organized system. Again, still a defined surface circulation, but this is when we have sustained surface winds between 39 and 74 miles per hour. It's actually an intensified system. Once we get to a truly intense system, once we reach the threshold, we call it a hurricane if it's over 74 mile per hour. But hurricane is the name that we give storms basically around the Americas, where we have the North Atlantic or Eastern Pacific Oceans. That's where we call it a hurricane. And again, sort of reiterate here, threshold for a hurricane, 74 miles per hour. That's the important thing to note when defining a hurricane. These are also, these same types of intense tropical cyclones are called typhoons in the Northwest Pacific Basin or severe cyclonic storms in the North Indian Basin. Some other basins, they're just generally referred to as still tropical cyclones and given some kind of intensity category to reflect its strong nature. Oh, skipped a slide there. Overall cyclone structure, there's really three main components of a well-developed tropical cyclone. There's the eye, which is the center of the circulation, which is a clear or mostly clear circular area of sinking air in the center of a strong tropical cyclone. It's sinking air, which causes the clearing, the lack of clouds there. And this is really what differentiates a warm core system, is that this warm center is associated with sinking air, and that's what forms the eye. But just outside of the eye is instead the most intense clouds, the most intense thunderstorms, the strongest part of the system in this circular ring that surrounds the eye. That's the eye wall. And then outside the eye wall, we still have rain and thunderstorms along bands and spiral rain bands that arc out from the center of the tropical cyclone. And if we look at sort of a cross-section picture of what this would look like, we have the eye in the center. Typically, the eye wall here, it's sort of a stadium effect, or it's slanted just based on how the dynamics of the system work out. We have our eye wall with our strongest pressure gradients, our strongest wind speeds, and localized heavy rainfall here in the eye wall, this really intense region right over here. This warm core is what we're talking about, is warmer temperatures aloft with the descending air in the eye. And then we have our spiral rain bands outside there, which even though they aren't associated with lowest pressures or the highest wind speeds, there's still localized heavy rainfall there. The last thing sort of talking about here in this last graph is storm surge. And we'll go more into detail about what that hazard of storm surge really is. But it's most intense on the right side towards the center of the system, because that's where the combination of the intense wind speeds of the system plus the movement of the system can force the ocean water to collect and build up in order to inundate coastal regions. And that's sort of what's depicted here, is the combined motion of the spiral, the circulation of the cyclone with the movement of the system means that your winds are strongest on this quadrant, this side of the system, towards the right side, because we're talking northern hemisphere here. So we have counterclockwise rotation of these low pressure systems. On the right side here, combined motion and rotation gives you strongest winds. So going to the where of tropical cyclone formation. Again, the name tropical cyclone sort of implies that these have to form in the tropics. The tropics in general, 0 to 30 degrees of latitude, both north and south. And they need to form in this way. They're tropical cyclones by nature because they are warm core, moisture-fueled systems. So they need that warm oceanic water and the balance of factors that occur in the tropics in order to form and maintain themselves. But one particular thing of note is that as these large-scale rotating systems, they can't actually form right on, or almost never can form real close or on the equator, because on the equator, the Coriolis force is minimal. So we need that Coriolis deflection in order to curve or spin these systems into a cyclonic rotating system. So 5 to 10 degrees north is the most common zone of formation because that's close enough to the equator that you get warm, moist air and warm, moist ocean water. But you're away from the zone right on top of the equator where you don't have enough Coriolis force. So if we focus in on those ingredients, we can talk about sort of the general ingredients for thunderstorms or general convection ingredient. These should be familiar from our past lectures about needing unstable atmosphere and moist air in mid-levels. But tropical cyclones come with some unique requirements. One is that these are oceanic-based systems, so they need warm ocean waters in order to fuel them, both at the surface and the near-surface layer, because the strong winds of these systems, as they grow and develop, tend to mix the waters. And if it's just a very shallow warm layer with cold water, you're going to quickly, because of the circulation, cool off the water and cut off the warm, moist air supply once that ocean water is in contact with the atmosphere. The other thing is weak vertical wind shear. When we've talked about thunderstorms in the northern hemisphere in past videos, we've talked about those needing strong vertical shear in order to organize. Tropical cyclones are actually the opposite. They need weak shear because of their dynamics are based around, instead of forming small scale systems with updrafts and downdrafts, they're large rotating systems that need larger scale heat circulations. And those can only maintain themselves and keep vertically organized when there isn't a strong wind shear. So the requirement for tropical cyclones is actually weak vertical wind shear. And might be another thing to recognize is we can't get something if it doesn't start somewhere. So we need a pre-existing disturbance. Most common form of these are easterly waves. So the general pattern in the tropics here tends to be easterly, and waves develop in that flow. This is also typically where the ITCZ, the Intertropical Convergence Zone that we've talked about in the past, forms. And if there's strong enough oscillations in that band, those are called easterly waves, and those can have enough cyclonic, enough vorticity in them in order to be a disturbance that can trigger off the formation of a tropical cyclone. Some less common but still notable disturbances that can trigger or start off a tropical cyclone include squall lines or mesoscale convective systems in the tropics, upper air troughs if it can dip down low enough to this region, or old frontal boundaries. Even though tropical cyclones are pretty much defined by their lack of temperature gradient, so lack of fronts, an old frontal boundary coming through a region of warm, moist oceanic water, forming an initial disturbance, initial convection, can be enough to get it started. So if we wanted to go through the process of what this looks like, in picture A here, we just have large-scale convergence associated with that initial disturbance, be it an easterly wave, part of the ITCZ, or an old frontal boundary, we get convection that ends up forming convergence. So we get towering thunderstorm clouds and converging air near the surface. But the circulation that gets set up is because we get this low pressure system here, we end up getting air circulating back around and actually warming and sinking in the center. That's what forms the warm core low circulation. And so once that develops, then we start getting this circulation and it starts reinforcing itself, because as this circulation gets stronger, we get more convergence, more convection, more warm moist air coming in, and it reinforces itself until we get a strong surface circulation, strong surface winds, a well-defined eye, and this strong warm core low system, which is, with strong convection around it, which is our tropical cyclone. So that was sort of the formation process. If we want to know when this tends to occur most often, here's a plot. This is focusing on the West Atlantic basin that impacts the U.S. a lot. The official hurricane season is June 1st to November 30th. Peak is in late August to early September. But as you can see from this plot, there isn't really anywhere except for maybe a few days over here, and the gap in the chart that's, sort of after the end of the year, the very start, where there aren't any. So most of the year there's at least a chance. But in the spring months is when they're especially rare. And the peak, again, late August, early September. Though, as you may have been paying attention recently in our current season, 2020, there's been a lot of systems in September and now recently November. If we go to where, talking about, again, that sort of West Atlantic or North Atlantic basin here, that's what gets a lot of attention in the US, because most of the landfalling systems in the US come from this basin, or most of the landfalling systems also in Central and the rest of North America. However, as sort of indicated by this track plot, most of these by frequency occur in the West Pacific. There's also a hot spot over here in the East Pacific, but most of these head off into the ocean and don't end up impacting places. But sometimes they do landfall, so they still are important to be considered. There's also, as you can tell, a lot more of these in the Northern Hemisphere versus the Southern Hemisphere. That's just a combination of where the land masses are and the ingredients, and especially because you need warm oceanic waters, where warm ocean currents are. These areas have relatively poor combinations of oceanic currents and atmospheric flows that tend to not support tropical cyclone formation. So if we go to dissipation, really dissipation occurs when we no longer have those ingredients for a tropical cyclone around anymore. One of the most typical, so probably the two most typical things for dissipation are having too much shear, and that's sort of what's indicated here. Not quite sure how this comes across on YouTube, but you have this well-defined circulation of a tropical system. It doesn't quite have an eye, so it's not as strong as some of the other ones can be. But you can see that these brighter colors are associated with high clouds. Those are pulled off in this more northward direction. But you can see it right about here. There's this circulation at lower levels where there's warmer temperatures. And that tends to happen if there's shear. So there's more southerly flow aloft and more westerly flow towards the surface, and that tears apart the system. It can't stay together because there's too much shear. The other thing that tends to dissipate tropical cyclones often is landfall, or going over cold ocean water. If you cut off the fuel source for tropical cyclones, which is warm, moist ocean water, no more tropical cyclone. The other thing is sometimes dry, stable air can cut off and weaken these types of systems, but usually when that happens, it's in combination of shear, and shear plays the first role. The other thing that can happen, and this is less of a dissipation note as more as it stops being a tropical cyclone, is if it moves too far north in the northern hemisphere, is typically when this happens, the Coriolis force can actually become too strong, and that changes the nature of the system's circulation. And it, instead of being a warm core low pressure system, it can turn into a cold core low pressure system, then become an extratropical or mid-latitude cyclone. And then you tend to get frontal boundaries developing, and it no longer has a tropical cyclone nature. But to iterate, the biggest thing that causes a tropical cyclone to dissipate or go away, strong shear or landfalling or going over cold ocean water. And this is the one little point I wanted to bring up since it's 2020 and we're talking about tropical cyclones, have to mention it. The Atlantic hurricane season this year has been record-breaking and in many different ways. And it's meteorologically fascinating, so you'll hear a lot of meteorologists talk with excitement about this kind of thing. But we also have to remember is that these systems, they don't all just strengthen and go off into the ocean. They do impact people, and there's a lot of tragedy and a lot of economic loss that come with that. So it's important to consider those impacts as well. It's sort of going over some of the biggest records here. It's the most named systems that there's been. Currently, we're at 30 with Hurricane Iota, which has just moved past 2005's record, which itself blew past most past records as well. It's also been the most active September with 10 systems, and the most intense late season, or this November, where well into the Greek alphabet on systems past the normal list of A through W names. We had Delta, that was a category 4, Epsilon category 3, Eta category 4, and now just recently Iota category 5, and all of these being rapidly intensifying systems where they go from relatively weak tropical depressions or tropical storms into these major hurricanes in the span of a day or two. So I mentioned those categories. That is when we get to these hazards. Hurricane intensity is categorized based on wind speed, the sustained wind speed in particular, and the scale is called the Saffir-Simpson scale. So again, 74 being the threshold for a hurricane, that's what brings us into the first category, category 1. We go all the way up to category 5 for the most intense hurricanes. Again, this intensity is measured based on wind. There's some debate in the academic community whether that's a good idea to tell our main number indicating the strength of a system based on wind, when wind isn't always even the primary hazard of a tropical cyclone. But we'll talk about those hazards in a little bit. Other hazards. Focusing on wind, again, these similar to talked about in past videos. What wind does is it can cause direct damage just by the force of the wind blowing up against structures, causing weakening, collapse in that fashion. But what actually tends to happen more often is once those initial damages happen, it tends to create debris, which is picked up in the wind, and those become projectiles that do even more damage. So these winds are nothing to be messed around with, especially once you get to these higher categories of hurricanes. Going back to the earlier plots of this lecture video, the strongest winds tend to occur in the eyewall region, and because of the combination of circulation and movement of the system, these tend to be on the right side with these northern hemisphere, these hurricanes. Safety tips for wind, really, the big one is stay inside the interior of a sturdy structure. Don't get caught outside. And the big thing, and this will show up in basically all the rest of these hazards for tropical cyclones, evacuation is usually the best bet when you're coming to these severe systems that have sufficient lead time. So storm surge, been referring to this a lot. This is severe flooding caused by a combination of, so you can get your high tide, that's just your typical typical oscillation of ocean levels near the coast, combined with especially the wind and pressure-driven water level rises that happen with tropical cyclones. And on top of that surge, you can also get high waves that come from these high winds that hurricanes and tropical cyclones bring with them. These are particularly notable in the US, where the Atlantic and Gulf coasts tend to be heavily populated and not very steep. So these get impacted by storm surge quite often. And in the US, really, these more often than not tend to have the greatest impact and damages from the flooding associated with storm surge. Really, with storm surge, it's a broad area. There's no avoiding it. It's to be safe, you have to seek higher ground. Or sometimes if it's weak storm surge, you can get away with being in the upper floor of buildings, but it doesn't really help if the building gets swept away. So in these intense storm surge situations, evacuating inland is the best bet. The other severe flooding contributor for tropical cyclones, it's not just storm surge, but these also can drop a lot of precipitation, heavy rainfall. The worst rainfall producers for tropical systems tend to be when they stall out and stop moving when they're near the coast. A particularly notable example of this was Hurricane Harvey back in 2017, contributed to major flooding in the Houston area. Safety tips for heavy rainfall associated with tropical cyclones: you can move your valuables and things away from the lowest floor. If your lowest levels do flood, you can move to upper levels of whatever building that you're in. But again, evacuation tends to be the safest bet because there's really no avoiding flooding when it happens. It's better to just get out of the way entirely. If it is flooding that through heavy rainfall, that's the main concern from the system, there may be flood mitigation efforts proposed by civil authorities. Participating in those is also a good way to help keep your whole community safe. But that's only with well-forecasted, anticipated systems that have flooding as their main threat and not things like wind or quick-moving storm surge. For those, go back to the standard safety precaution for tropical cyclones, which is evacuation. Lastly, hazard of note is tornadoes. These are less common than the wind and flooding threats, but tornadoes can and also do occur with tropical cyclones. They're generally less intense than the tornadoes that we talk about in Tornado Alley or Dixie Alley, central United States. But when these are added to the larger areas of hurricane force winds, it can produce notable damage. And they're typically what can explain these uneven damage patterns where you have your overall damage from hurricane or tropical storm force winds, but then you have particularly small but localized areas of catastrophic damage. That can typically be explained by tornadoes occurring within the tropical cyclone. Most common areas for these are the right front quadrant, again, kind of our most intense area of hurricanes. Or tornadoes can also be embedded in supercells that occur in the rain bands of these systems. If there's enough storm scale dynamics going on, you can get supercells and tornado producing storms in the rain bands as well. So wrapping up this video, again, another unfortunately a little bit longer one because a lot to go through on this topic. I wanted to say a continued apologies for all the weirdness and lateness of the schedule on my part. It's been quite a humbling experience to try going through and still teaching this course and doing everything through difficult personal circumstances. So I apologize for any difficulties on your end, but I'm very appreciative for you working through and being patient with me in this. I wanted to mention the remaining assignments for the course are the week 6 quiz, which was extended both in nature due to all of this lateness to Saturday 21st. The week 7 discussion post, that's just on normal schedule. Initial reply due Thursday 19th, reply due on Saturday the 21st. And the final project that's been anticipated since the syllabus was released, due Wednesday 25th at the very end of the course. On any of these, I want to be as understanding, both, accommodating for my failings to have the schedule I had promised to all of you, and just the general difficulty of our times. If you need more time on really any of the preliminary assignments or anything that's out now, there won't be any penalty if you get things really at this point turned in by the end of the course. It might still show up as late in Canvas, but it's not going to be penalized. But again, that Wednesday 25th has to be a hard deadline because that's when the course ends on Canvas. So unfortunately, if you can't get things in by then, may need to be in contact about some kind of temporary incomplete grade until things can get worked out. Last thing is that there will be lecture videos still coming out in the next day or so on winter weather. I need to get on and get those together, but those will not be quizzed on, and they're really for your own education. And if you are still needing a topic to finish up your final project on, and you aren't going to look for another university or NOAA or government source for this information, you can feel free to use those lecture videos on a winter weather topic for your final project as well. So with that, I thank you and look forward to, if you're interested, seeing you on the winter weather lecture videos as well. Thank you.